Hey guys, hope you're doing well. We are going to start our next unit, which is a unit that's going to focus on one type of energy called heat energy. So we finished up with our units that were kind of about physics, motion, and machines and work. And we're going to be moving on here and starting to talk about a couple of units that are related to energy. So that's where we're going to be starting. I just noticed I could use a haircut. But anyway, let's start off here. There's a couple versions of blank notes for you that I posted. One has 2 slides per page that we usually use, and the other has actually 4 slides per page. So if you're trying to save ink and paper, you can use that one. Your parents probably appreciate it. So we're going to start here just by talking about something very general. And that's about sort of the differences between matter and energy. So basically, in the universe, everything can be categorized as either matter or energy. And so much of what we've talked about so far is about matter. It's about materials, molecules, atoms. Okay, so matter is defined as something that has mass and volume. Has mass and takes up space. So when we talked about chemistry, we were talking about atoms and molecules. Okay, that was about matter. Or in the universe, things can be energy. Energy is not. Energy is a form of it's hard to define energy. Energy, it can be either classified as kinetic or potential. Energy is the ability to do work. For example, kinetic energy is energy of molecules that are moving. Okay? And all materials that are above what we call absolute zero have kinetic energy. The molecules in them are moving. Okay? Water flowing down a stream is kinetic energy. A roller coaster traveling on the track, that has kinetic energy. Throwing a ball, that has kinetic energy. Moving a weight using a machine, that's kinetic energy. But objects can also have potential energy. Potential energy is sort of stored energy that can be used later on. And potential energy can take different forms. You could have kinetic energy in the form of, water that's being held behind a dam. So that water behind the dam, it has the potential to do a great amount of work. Okay, if you allow that water to move through the dam and allow that energy that's stored there to be transformed into kinetic energy, that energy can then be used to do work, to generate electricity or to power a mill or something like that. Batteries, for example, also, they have potential energy in the form of chemical energy that's stored. And when a battery is connected, then the energy that's stored, that potential energy, can be used to do some useful work. So when we're talking about matter and energy, there is a law that's called the law of conservation of matter and energy. And the law of conservation of matter and energy, we talked about this a little bit in terms of matter, but it also applies to energy. It says that matter and energy cannot be created. Okay? We can't just create energy out of nothing. We cannot create matter out of nothing. We also can't destroy matter. We can't destroy energy. Well, then what can we do? Well, we can transform matter and energy from one form to another. Taking that piece of paper and burning it takes one form of matter, the molecules that make up the paper, transforms them into other types of matter, carbon dioxide and carbon monoxide and water vapor. So we can transform that matter. We're not actually destroying it. The same goes for energy. We could transform chemical energy into electrical energy. We could transform potential energy into kinetic energy. Okay? But we can't destroy or create energy. Okay, so it can only be transformed from one form to another. In this unit, we're going to be focusing on heat energy. So heat energy is the energy of moving molecules, vibrating molecules. If you say the desk you're sitting at or the counter you're sitting at, okay, that's made of molecules. And even though you can't see it, the molecules that make up that desk or that counter, those molecules are actually vibrating in place. Okay. And the energy of those vibrations, we call that heat energy. And if we heat up a substance, what happens is those molecules that are vibrating start to vibrate more quickly. And that's what happens when we add heat to a substance. Now, typically when we heat up a substance, what we see is that the molecules vibrate faster, but they also spread apart. That process is called thermal expansion. When you heat up a substance, generally it expands. Okay. And if you cool it down, then it contracts. Its volume increases or decreasing with the temperature. So if we look at, imagine a solid that's cold, the molecules are relatively close together. As we heat it up, the molecules move faster and they also expand. We talked about this a little bit in our density unit because we said that as we heat up an object, typically the volume increases, but the mass stays the same, and that causes the density to decrease. So to measure a temperature, we use a tool called a thermometer. So a thermometer, like a traditional thermometer that you might see, has in it a liquid. Sometimes it's mercury, but not so much anymore because mercury is toxic. It typically might be alcohol, a liquid. And as that liquid that's held inside of that thermometer warms, it expands. And because it's in this enclosed space, the liquid, which is colored usually, moves up the glass, and that's marked to show certain temperatures. And that's how a thermometer works. Now, nowadays, we might have digital thermometers that have a sensor to register the temperature of a surface. You might have a thermometer you put in your mouth but has a digital readout. But you might see these thermometers, maybe if you have like a candy thermometer that you use for baking and things, it might have an actual, it's called a bulb thermometer with a liquid in it. We had to be using these in the classroom. If we were in school, we would do several labs in which you're going to be measuring the temperature of a substance using a thermometer. But we don't have that right now. So inside of the bulb, there's this liquid, and as it heats, it expands, and it rises up the thermometer, and the markings have the equivalent temperature. So if you've ever been sort of walking along the railroad or seen a railroad track, you may notice that often between the rails at various intervals, there's a gap, there's a space between the rails. And there's a reason for that related to what we've been talking about. And it's due to thermal expansion. So because a railroad track needs to be working in the summer and the winter, and in our area, there's pretty wild temperature fluctuations. When it's summertime and it's really warm out, what's going to happen to the metal of this railroad track? Well, it's probably going to expand. And having that gap between the rails gives the railroad track some room for expansion. Here are some other examples. You might see these sometimes. These are found on bridges oftentimes. So a bridge, let's say, that crosses like the Hudson River, okay, where two sections of the bridge merge, rather than being connected as just a solid piece of metal, they often will have these sort of fingers that kind of weave into each other. And what happens is when it's cold out and the bridge contracts, those fingers can pull out because the panels have contracted, but not completely separate. In the summer, as the temperatures get warmer and the pavement and the metal expands, there's room for those to expand without buckling. You see the same sort of example here in this railroad track where it's not quite a gap, but there's those panels overlap somewhat and they can expand or contract. If they didn't have that, you can see here in this picture that these railroad tracks have buckled because those expansion joints were not working or were not present. And so when the railroad track got heated up, the track actually buckled. You may have heard about people saying when you take, if you have a jar and it's difficult to get the lid off, it's too tight, if you run it under hot water, the idea is that the metal of the lid can expand slightly, loosening it and making it easier for you to open. And you see this, there's some videos that are kind of neat that often in reconnecting railroad tracks or repairing them, often they heat up the railroad tracks. In this case, this was a railroad track, because it got so cold, the rails contracted so much that they were completely separated. And so one of the ways of fixing that is they take a rope soaked in oil, lay it along the track, and then light it on fire. And the heat from that will actually cause the tracks to expand to sort of reconnect. So when we want to measure the temperature of a substance, we use a tool called a thermometer, as we talked about. And there's a few different scales that are used when discussing the temperature of an object. The one you're probably most familiar with is the Fahrenheit scale. The Fahrenheit scale is sort of the English scale or the customary scale that we use. We use it in the United States, and it's not really used many other places. Most countries, if you travel around the world, use Celsius as their typical temperature that they use for weather reports and things like that. For us, sometimes it's hard to kind of to relate to the Celsius scale because most of us have grown up always thinking about temperature in the Fahrenheit scale. We sort of relate to that. Like, you know exactly, if I tell you it's 100 degrees Fahrenheit out, you really know it's really hot out. Or if I tell you that it's 3 degrees Fahrenheit, you know instantly what I'm talking about probably. You may not quite have that same comfort level with the Celsius scale because we don't use it as much. But that would be the scale we typically would use in science, or we might use the Kelvin scale. And we'll talk about that. So you should know a few of these temperatures. Okay, so normal human body temperature. So we typically think of normal human body temperature as 98.6 degrees Fahrenheit. The equivalent is 37 degrees Celsius. Now, actually, it's sort of interesting in that recent research shows that over the last century, average human healthy body temperature has actually declined and dropped somewhat. But we're going to consider normal human body temperature 98.6 Fahrenheit, 37 degrees Celsius. If we think about a room temperature, obviously the temperature of a room can vary, but what we typically think of as about 68 degrees Fahrenheit is typical room temperature. In Celsius, that's 20 degrees Celsius. Freezing point of water, you probably know in Fahrenheit, it's 32 degrees Fahrenheit. That's the equivalent to 0 degrees Celsius. The boiling point of water is 212 degrees Fahrenheit or 100 degrees Celsius. And as we talked about the metric system, obviously the Celsius scale makes more sense. 0 and 100 were set as the set points where when water freezes 0 degrees, water boils 100 degrees, and that sort of makes sense. Where did the English system come up with 212 and 32 degrees Fahrenheit? I honestly don't really know. There's another scale called the Kelvin scale. And the Kelvin scale is sometimes also used in science and research. And the Kelvin scale is set up so that 0 degrees Kelvin, okay, is called absolute zero. And so if we think about temperature as the movement of molecules, and as we cool down a substance, the molecules move slower and slower. Well, maybe you've thought of this. Well, if you cool something down enough and you make the molecules move slower and slower and slower, eventually, maybe the molecules stop. That point at which molecules basically stop moving is called absolute zero. It's 0 degrees Kelvin, negative 273 degrees Celsius. And that's a temperature that scientists haven't really brought material down to the temperature of absolute zero. They've gotten very, very close, but absolute zero is basically the coldest that any object could theoretically get. So when we talk about temperature and we talk about heat, we're not really talking about the exact same thing. So temperature is a measurement of heat. You're measuring the temperature of something, you're sort of measuring the average energy of a substance, the average kinetic energy of those molecules that are moving. And then we think of heat as an overall total amount of motion within that substance. So sort of like the total versus the average. So to help understand this, if we imagine two substances, let's say we had a glass of water that was at 50 degrees Celsius, okay, a glass of hot water, and we had a 5-gallon pail full of water at the same temperature. So they would have the exact same temperature. Would one of them have a greater amount of heat? Yeah. The 5-gallon pail of water would have a much greater amount of heat. Because heat depends on two things. It depends on the number of molecules there are and the speed of those molecules. So temperature is a measurement of heat energy. So as we think about this, okay, if we have 2 liters of boiling water compared to 1 liter of boiling water, the 2 liters will have twice as much heat energy. But how will their temperature compare? Well, they'll be the same. They're both going to be 100 degrees Celsius. Here we have another example. So we have water that's 40 degrees Celsius. We either have 500 milliliters or 300 milliliters. If you were to measure the temperature of each of those using a thermometer, they'd show the same, 40 degrees Celsius. However, beaker number 2 has a greater amount of heat because it has more molecules. Okay? So if we look at a metal bar here, if it's at 30 degrees Celsius, okay, this metal bar has greater amount of heat than this metal bar or this, because even though it's the same temperature, has double the molecules. This metal bar and this metal bar, they have the same amount of heat, at the same temperature and the same number of molecules. Okay, so that's sort of overall idea about heat versus temperature. When we are discussing different substances, we can talk about one characteristic of those substances is their specific heat. And basically this is a measure of how much heat do you need to add to something to actually raise its temperature. Different substances have a different specific heat. Water is a pretty high specific heat. What that means is it takes a lot of energy to raise the temperature of water compared to other substances, and it resists changes in temperature. Okay, and you may understand this in that if you go like in the springtime, for example, if you go to the beach, say you go to Myrtle Beach, South Carolina, during spring break, the temperature outside can get pretty warm. It could get about, maybe 75 degrees Fahrenheit. However, when you go in the ocean, it's much colder than that. Okay, the temperature might be down at 60 or 65. That's because it takes a great amount of actual heat to raise the temperature of that water. Okay, the water resists that change. Or if you go in a pool, say you have a pool and you go swimming at night, say it's been a middle of summer, okay, nighttime comes along and it cools down outside, but if you go in the water of the pool, you might find that it's still warm, okay, because it's retaining that heat from throughout the day, and it takes a long time for it to cool off. It's also why cities and areas that are near the oceans have a milder climate typically, that they don't have temperature fluctuations as much as inland areas, because that water that surrounds them is moderating their heat. One unit that we use when we're talking about heat is the unit of the calorie. It's a unit of heat, and it's the amount of heat. 1 calorie is the amount of heat that is needed to raise 1 gram of water 1 degree Celsius. Okay, so calories are measurements of energy and heat. And when we have substances of different temperatures, heat will always travel from the warmer object to the colder object. So if we have 2 containers of water, one is 50 degrees Celsius, one is 20 degrees Celsius, okay? If we were to combine the 50 milliliters, okay, of 20 degrees Celsius water with 50 milliliters of 40 degrees Celsius water and mix those two together, they're the same amounts. What do you think the final temperature would be of that 100 milliliters? It would be 30 degrees Celsius. Okay. And if we put these 2 objects next to each other, the warmer object heat will be transferred from the warmer object to the cooler object until they've reached the same temperature. Okay. If I take a flask of hot water, put it inside a beaker filled with cold water, the same thing would happen. Even though the water's not going into, the waters aren't able to mix. These are closed systems. Okay. The flask of hot water, the heat from this flask of green hot water would be transferred into the colder water. Until when? Until they reach the same temperature, until they reach what we call equilibrium. And if you hold a cup of hot water in your hand, the heat from that cup is going to go into your hand. Okay? Or if you were to hold an ice cube in your hand, the heat transfer would be the opposite. Your hand is warmer than the ice. Heat from your hand would go into the ice and would eventually cause it to melt. And so if you put let's say you put a glass of room temperature water in the refrigerator, what's going to happen? Is the refrigerator going to put coldness into your water? No, it's not the way heat transfer works. What's going to happen when you put your glass of room temperature water into the refrigerator is your glass of water is going to lose heat to the cool air in the refrigerator, and therefore the temperature of your glass of water is going to decrease. It's going to decrease until it matches the temperature of the refrigerator. Can that glass of water ever get colder than the refrigerator? No. The coldest it's going to get is the temperature of the refrigerator. So that's the end of our first section of notes here, just about sort of heat and temperature in general. Okay, we'll have some review for you to reinforce some of these ideas, and in our next set of notes we're going to be talking about how heat is transferred from one place to another. So I hope you guys have a great day, and we'll talk to you soon.